first of all, what is a synchronizer? What do you understand by the term synchronizer? Any one of you can answer? From Goa also? See, we normally talk of a synchronous system design. That is what normally is designed also. Okay. So it so happens that sometimes you get an input from a keyboard, which is asynchronous, which can come at any point of time, which is not aligned to the clock edge. Now this can come and it has to now go into the system and should lead to a valid output, valid system output. Now it so happens that while it is fed, since there is no timing of it, it can come at any point of time. Since there is no timing attached to it, it can come very close to the system clock edge. Now think of a data path which is say positively edge triggered, and suddenly an input comes which is after the T setup, which gives you a T setup violation or a T hold while. As a result, now we have for every, because every system has to go through a flip-flop, a pipeline system, okay? So naturally it is violating either a setup time or a hold time. Now what can happen if there is a violation? Why we say violation should not happen? What can happen to the system? Why do we at all define this metric T setup, T hold? What may happen if there is a violation coming up? What is metastability? So if something comes within that window of T setup hold, as you said, that metastability result, because your output might not have reached the full logic levels. Since within that period system state is not known, input state is not known, so this value is unknown. It is something which is not very clear to us. It is confusing. Whether it is logic 1, whether it is logic 0, is it if it is more than switching threshold, less than switching threshold, we don't know. It is between VIH, VIL. I don't know what this value is. It can be anything. So your next system to which it is being going as an input, it may treat it like a input 1. It may treat it like an input 0. As a result, if this input is going to multiple systems, multiple blocks, every block will interpret it in its own manner. As a result, they will produce an output. Since all are not looking into it in the same manner, system output will be illegal. This is not a known state that you should have, because different outputs are coming because this signal is interpreted differently by different blocks. And this can lead to system failure. And then you have to have the system resetting will happen. There is a complete routine protocol which is followed by the system the moment there is an illegal state coming up. So it has to go back, reset itself, reset its flags, everything. And then again it will take some time to come back to its original state, and then we have to input this value again. So this will cause a system lag unnecessarily. System is getting delayed. And we do not want this to occur too frequently. We do not want this to occur too frequently. As a result, we do not want any kind of interfacing problem between asynchronous and synchronous interfacing. Now this I have given you an example of a keyboard. Now it can happen in a different fashion also. Now you may know that in a system, I may have a multiple clock domains. Nobody says that all the blocks, they should operate at the same frequency. Now we all know that to save frequencies, to save power, if certain block is computing early, what actually is done is that we make it to operate at a lower frequency so as to save on power, so that by the time the latest output comes, this output would also be ready. It need not compute so early and then remaining idle. So we can have multiple clock domains in our circuit. And because of these multiple clock domains, they would be talking to each other. They would be communicating with each other. So this may have a different edge triggering frequency. This may have a different, and the moment this one talks to this one, again the same problem can happen. The signal coming from this block or one of the block may not be aligned properly with the clock edge of the next. Again, because they are operating at a different frequency, the same problem can happen. The same problem can happen in a multiple clock domains. So whenever we have such kind of a problem coming up, and there is a chance that system can go into synchronization failure, I now look at this problem, analyze it, and then design a synchronize, which guarantees whatever happens, system will never go to a failure state. Because we do not want a failure state. A failure state is additional timing overhead. And if it is occurring too frequently, naturally, nobody would like such a process. So definitely we want the mean time between the two failures. I want this to be infinite. So that if today one failure has occurred, the other failure should occur after infinity time. This is ideally, even if it is not ideal, maybe years, 15 years, 20 years, so that by the time the processor would have aged out, I might not be using the processor at all. I hope you all have understood the problem of metastability. So here comes the need for designing a synchronizer, which is actually nothing but a D flip-flop. Because whenever you design or whenever you feed an input, it first goes to a flip-flop, a D flip-flop. So actually modifying the D flip-flop so that it does not lead to a synchronization failure. Now, lesser than this problem is a synchronization error. Error means system is not going into a illegal state. Maybe it so happens that it is interpreted wrongly. But then it still comes to a valid state, which is a known state. It is not an illegal state. But because it is interpreted wrongly, the value should have been 1, you are getting a 0. But it is a consistent thing. All blocks are behaving consistently. Okay, so this is known as a synchronization error. So synchronization error is less a problem than a synchronization failure, because once system goes into failure, it takes time to come out of it, which we do not want. Whereas such thing doesn't happen. Only thing we need to do is we need to re-input our value because there is an error reported. We need to give our value, and then according data will be like it would be, output would be corrected. Okay. So this was actually, nobody was knowing about it till 1970s, when a thorough study was made, and metastability was causing systems to fail. So in 1970s, early 1970s, two scientists, they did a thorough study of it, and then they reported that major problem is a synchronization problem, which should be avoided, and hence then a lot of focus went into designing of good synchronizers. So a good synchronizer is actually nothing but a kind of an arbiter, where you have two competing inputs. Here you have also two competing inputs, like one is the clock, other is the data. They both are coming so close to each other that things are becoming out of control. In arbitration also, like a bus arbitration logic, suddenly you have a request coming from two slaves, requesting for a master bus, and then you have to resolve which is to be given. So it is the same thing. Here we again have to resolve whether to input the data or we have to hold it. If we are not sure the data is fully resolved, we will not allow it to pass through, so that we do not want my system to go into a failure state. Okay, so here we have to take a decision. So here my two inputs will be clock and the asynchronous input or input coming from another clock domain, where in the case of a bus arbitration logic, it is usually two requests coming for bus access at the same time. It's more or less the same thing. So here is something that we all understand. It's a typical curve that we should all understand about the metastability. That for any flip-flop, you have the clock edge represented at, or it comes at t equal to 0. Then before th, t equal to 0 instant, there is a duration which we call as a t setup, and there is a duration which we call as a t hold after the clock edge. And the clock edge we are assuming is a nominal clock edge arriving at t equal to 0. So how do we understand metastability is that if your data is coming before in this domain at this time, it is stable. So the time taken by the flip-flop to which it is being fed, it is a bounded time. Within a known time, it would be able to pass on this. So can you see the response time is lesser value? Okay, but as it is approaching and it is heading towards the metastability window. This is called as metastability window. From t setup to t hold, here if the input comes, okay, very close to clock edge, that response time becomes unbounded. Then the flip-flop doesn't know what it is. Input 0 or input 1, I don't know, I'm not able to decide. So here the response time is unbounded. And then again, if this passes away, input comes somewhere here, naturally clock edge has already passed out. So it can only latch into the next clock edge. By that time it would have stabilized. So my response time is again a bounded response. So very typical metastability response that you should all understand. And based on that, all our equations are, all our analysis is decided. This is the simulated result which confirms the graph which is decided or shown in this. You may check on your own a simple D flip-flop you can make or D-latch, and then try to give an input which is coming within the metastability window and try to look at the output Q. Okay, this is you should get or trace a curve as shown like this. Okay, so now how do we understand? So naturally it is nothing but a D-latch. It's going to be a latch. Understand it? The synchronizer is going to be a kind of a modified D-latch. Okay, output will be if the D input is coming very close to clock is this. Okay, your output is, can you see? Q is not able to either charge or discharge. It is remaining somewhere in between, and to rise fully up and fully down, ultimately it will rise completely up, fall down completely. But then it will require infinite amount of time. It will ultimately go. Why? Because there is always a noise present in the system. It will ultimately stabilize to one particular point. But then do we have time to wait till that much amount of time? We cannot allow my D flip-flop because I only have one clock cycle. Within one clock cycle, either you give me the input or you leave the input. Because otherwise, the system cannot keep on waiting. The system cannot keep on waiting. So either you latch in the data or you don't latch in the data. You take decision immediately, but you have only one clock cycle available to you. So we have to find one clock cycle solutions. We have to find one clock cycle solutions. So now to understand, as normally if you have a master slave configuration of a flip-flop, so naturally the first one, whichever has the input is naturally is going to face the metastability problem. It is not a problem for the slave. Slave is simply acting like a buffer. It's mainly the first one to which the input is fed. And you have a setup and hold time violations over there. Okay. So first of all, the very first thing I will say is that I will try to find out I will try to analyze this my D-latch. I will try to analyze this D-latch and try to find out this metric which we call as a mean time between failure, MTBF. And we will try to see that how can we make this MTBF very large. How can we make this MTBF very, very large, and based on that our designs will start coming. So first of all, we will try to derive an expression for MTBF, which is going to be the guiding light for me to design my synchronizer. So mean time between failure. So on what components it depends. Okay. So suppose it is a D-latch. What is a D-latch? It is nothing but a simple D-latch is a pass transistor followed by a cross-coupled inverter. A very simple D-latch. I am not looking for a two-stage configuration. A simple D-latch like this. Okay, so this is a core element which is producing my Q. So if this data coming over here is not proper, naturally the Q will not, we will not know what Q is. Okay, so we will try to analyze this I1, I2 bistable element pair. So I try to develop a small signal model of it. It's a cross-coupled inverter with this characteristics. Okay, so we try to develop a model of it. So you have to now visualize two inverters connected back to back. Okay, so one has parameters designated by subscript 1, other has parameters designated by subscript 2. We are developing a small signal model. Output of one, output of second is the input of the first. Accordingly, this model has been developed. Okay, this is GD is R base or RO. C1 is the net capacitances. Okay, and GM1 VGS, the component is known. So we have developed a complete small signal model of this is known as a recycler. This is complete model is developed, and then we write its KCL equations. We write its KCL equations, and then we solve. Then we solve it by using mathematical relationships, and we get the solution as V1. V1 is the output of first inverter, which is the deciding the output of the second inverter. At any point, there would be two outputs, V1 and V2, so you can write equation in terms of any one. Okay, because one will be deciding the another. So I get the expression for these two equations. The solution comes out to be in this form, where Ka and Kb will be the parameters related to voltage parameters related to initial conditions. Okay, and then there would be time constants of each one, because every inverter has a time constant, RC. Every inverter has a time constant, so accordingly the TA and TB is coming from there. The general solution for these equations that we have derived, you may resolve it, solve them, it comes out to be this. Now once we have that, you can find just at the moment of, I can have two boundary conditions. One, what is the status? Just the moment of metastability. That is at T equal to 0th instant. And at T equal to infinity. Two possibilities are there. Okay, so just at T equal to 0, when I substitute in this equation, okay, just at T equal to 0, we get the V1 value at T equal to 0 given by this. It would be Ka plus Kb, okay, which is given by this. Both will be 0, 0, so it is simply Ka plus Kb. Okay, you may keep them with you. Then second is we have for T tending to infinity. What is the condition at T tending to infinity? So when we put T tending to infinity, my equation now changes. V1 value changes to a metastable value, which will happen at T equal to infinity, which we do not know currently. We write it as V1 metastable. We write it as V1 metastable, and our equation now T I have to substitute with infinity. Minus infinity will go to 0, so this term goes away. It is only e to the power T by tau B. Okay, clear? Now here is something. Now this is a very, very important. Why am I looking at the second one and not the first one? Why? Because I am interested in finding the behavior at T very large. Because metastability is happening only at T very large. Unboundedness is coming into picture only at T very large. It is not getting stabilized. It is taking infinite amount of time. It is taking initially in the beginning. It's only input value that you would be getting, which may be, which you might be getting at this node, at this internal node. How is this Q behaving with respect to time? Okay, so behavior of Q with respect to time is shown in this simulation plot. So Q is, can you see, depending on what your initial V1 at T equals to 0. So depending on where you are you closer to VIH? Are you closer to VIL? Or are you in between the two range VIL to VIH? Can you see that this one is taking the longest time to this one? Whereas if you are closer to VIH, very soon it stabilizes to a high value, and if you are closer to VIL, very soon it stabilizes to the 0 value. So wherever you are at t equal to 0, what is your value at t equal to 0? That will decide how much time you are going to take. And the problem comes when you are somewhere in the middle. So remember, the range of metastability for me, which is actually according to me is between t setup to t hold, actually coincides with the range VIL to VIH of my bistable element. It coincides with that range, VIL to VIH of my inverter. Because only in that range it is in a transition state. It is unknown to me. It is okay. So depending on those values, if you have certain capacity initially, voltage across the capacitors, okay, that will decide these voltages. These Ks are actually the voltages. These Ks are actually the voltages. So those initially, if your capacitors are initially uncharged, accordingly your values would be coming in over here. Okay. For metastable event, okay, this equation is going to play a major role. And from this major role, the voltage that you will be getting, can you see it is going to be a value which is slowly, can you see this Kb is actually a parameter which is slowly decaying with time. Or voltage is slowly rising, exponentially rising with time. It's not that voltage is static. It's not. Voltage is rising. It is rising, slowly rising, and slowly moving towards its final value. It is rising. But it is exponential distribution. And that exponential distribution has its own time constant. It has its own time. Okay? And the more I wait, more I have the chance that system will stabilize. More waiting time I give to my this D-latch, there is a more chance that system will stabilize. There would be no failure happening. That means if I try to find out the probability of failure, that is inversely proportional to this exponential rise. That means if I give t increasing, if I say more and more waiting time, t goes on increasing, my voltage will keep on getting stabilized. That means my probability of failure would be less. So this equation actually gives me or takes me to the expression for a probability of failure, which I would be using to find out MTB. So what is the probability of failure? I can now very safely say from this analysis that it would be exponentially falling as my t is increasing. Here t is the time I am allowing to the system to stabilize. The more time I am giving it, the more it will have a tendency to stabilize. Less is the chance for getting a failure. Okay, so one thing is very clear to me through this analysis, that this exponential distribution will be a part of my probability of failure expression and will find a place in MTBF expression. It will find a place in NTBF. Yes, there would be other parameters also. But this analysis I have particularly done to find the the profile. The profile of my probability because I cannot take just any profile. I could have taken a kind of a square rooting or square or anything else, which I should not do. I should at least go in a very methodical manner. That's why this analysis helps me, that you have to take a exponentially falling profile for determining the probability of failure. Okay. And then naturally for this expression you will get the value for Kb also and the value for your time constants also. Maybe you can find out these values, the V1 metastability and V1 actual simulations, plug it in and get the values for K, Kb, etc. And then put in these values and get more precise expressions. Okay? Rather than doing it manually, your simulations can help you out over here. So this is again another type, but I think now probability is something very clear to you. So now we come to the probability of failure. So when we say probability of failure, two things are very, very necessary. First of all, your input that is coming should come within that window. Set up to hold time window. It should come within that range. Because input can change anywhere. Metastability will not happen everywhere. Metastability will not happen. I have to ensure that metastability can happen only when there is a violation. Metastability window violation. So what is the probability that input data will change during this window? So your total time span is T hold to T setup, and your total time cycle is T clock. In your T clock, it can change anywhere. Nothing will happen. The moment it happens within this range, a metastability is bound to happen. So the probability that your input data will change in that window is simply a simple relationship. It is this time slot divided by the total T clock available to you. Divide by the total T clock. So this comes out to be T hold minus T setup by T clock. If the input is not changing, this probability would be 0. There would be no metastability. Okay. So now this is one equation that I am getting. This I am calling as a window W interval. And this is your T clock means system at which system is operating. To which you are feeding the asynchronous input or input coming from a different clock domain. Okay. So this now F clock. So W into F clock. Okay. Now your data, as I said, may not be fully asynchronous. As I said, even with asynchronous input, I can find or I can attach an average arrival frequency to it. When you are typing, you have an average frequency at which you would be feeding in the new input. You can always compute. Or the input is coming from a different domain. It has its own data frequency at which data is arriving. Okay, so it is not that. So now that input, probability that input will change. At what frequency your input would be changing? That is your data frequency. One is the clock frequency at which system is operating. Second is an input which is coming from somewhere, is again coming at a certain rate. That I am calling as a FD. I am calling it as a date. So what is the probability that it has come into that window? What is the probability that there would be a metastability? Understood? There may not be a metastability. In how would you define a probability? Yes, there would be a metastability. It has entered into that window. It may or may not lead to failure. Then what is a definite condition or probability that it will lead to a metastability? It will lead to a failure. So the total probability will be multiplication of. I want 100% chance for metastability to happen. I want 100%. So I find two probabilities. First of all, the probability that input will change too close to the clock edge. Okay, and secondly, that what is the probability that even if it has come in that, it will lead to metastability. So I find out that the rate at which it will enter metastability. Now it will also depend on the data frequency, not only the clock frequency. It will depend on the simulation setup window. Okay, so here is you have the total. You can say the rate at which it will enter into the metastability probability is I have to multiply this expression by the data frequency. How frequently it can move into the metastability. How frequently? That depends on the data frequency. How frequently it is coming. Okay, so it is simple W into FC into FD, and then we say, okay, these things I know. Now the probability that there would be a failure, it depends on an exponentially decaying profile, the waiting time. There would be no metastability if there is a sufficiently large waiting time. Okay, so I now need to multiply the whole value that I have just derived with the term e to the power minus t by tau. The tau is your time constant of the system, or the delatch, and t is the time you are making it allowed. Wait, keep on waiting. Okay, I am installing my system, you keep on waiting and resolve the metastability. So larger time I give, smaller will be the probability. Larger time I give, smaller will be the probability. So I have now W into FC into FD, which is to be multiplied by this e to the power minus t by tau, where t is normally going to be 1 t clock, because I cannot give you a time more than 1 t clock. I cannot give you a time more than 1 t clock. Or if you are giving, that means you are stalling the system. Then you are stalling the system. So the total probability that you will enter metastability, and once you enter metastability, there would be a failure. There would be, it will lead to failure, is given by this expression. It is given by this expression W into FC into FD e to the power minus. This gives you probability of failure. The system can enter into a failure mode. For t more than 0 means I am assuming that clock is coming at t equal to 0th instant. So now if probability is less, that means mean time between failure is just the inverse of it. Mean time between failure is more. So MTBF is simply the inverse of the probability of failure, which is given by this expression. So it depends on W. So make your T setup T hold window very small, so that MTBF increases. Operate at very low F clock, or operate at a very low F data, or give enough waiting time. So now from this expression, I want MTBF to be as large as possible. That if today one failure has occurred, next failure should occur only after 20 years. How do you design? Whereas my constraint is 1 clock. As far as possible, 1 clock solutions. I have a 1 clock solution. Understood? Everybody has understood? So MTBF concept is clear to all of you. So the synchronizer phase, when data is sampled in that window, sampling window, and then it gives the output response longer than, in a time longer than the resolution time allowed. It does not give you a stabilized value within the time allowed to you. Okay? So this expression is now very critical to us. Remember that. So now you may just go on like making some more calculations. So suppose you have a where you have some number of synchronizers. Okay? And we say that SOC will fail if at least one of the synchronizer fails. Okay? So again you can find out the probability that, what's the probability that SOC system on chip will fail. If there are K synchronizers, because I will not have only one synchronizer in there. You will have multiple synchronizers because it's a big system. You may have multiple synchronizers over there, and we say, okay, I do not want even a single synchronizer to fail. Because one synchronizer fail means a system going into a failure mode, which I do not want. What's the probability that system will fail? If there are, say, n number of synchronizers over there. So that's a small analysis over there. So we find out the probability that system will fail is given by this expression. So probability that system will not fail is simply 1 minus this, or synchronizer will not fail is 1 minus this. And if there are K synchronizers, it to the power K. It would be simply to the power K, and the probability then that SOC will fail is simply 1 minus of this. And then you will get an MTBF for such a system where there are K synchronizers. What's the MTBF of such a system where you have K synchronizers over there? What's the probability system will fail? Because if any one of them is fail, the system will fail. So a little bit of manipulations with the previous result to arrive at a generalized expression for my MTBF. Okay. So now let us see. Rabbi, as I said, ultimately your T set for T hold actually relates to VIL to VIH. So your textbook Rabbi takes a little bit of different approach. He tries to analyze your bistable element from the point of view of switching threshold, VIL, VIH. and then again comes to an MTBF expression. He again comes to an MTBF, and then we will see ultimately that when you combine and compare the two, they are actually the same. Okay, he again does the same analysis. He does a bistable element analysis. This is what he says. He says that a data clock edge, okay, and then data is not fully resolved. So when it is sampled, it is somewhere here. When the data is sampled, the orange line, red line is a clock edge. So when it is sampled at this edge, it's an edge triggered system, suppose. So when it is sampled, your data is not fully resolved. It is within the range VIL to VIH. It is within this range. And he says, assuming it is not exponential, it is a simple linear rising. Just for the sake of ease of model. He assumed this is linearly rising, and the time to rise from minimum to maximum is T rise. Okay, and then this is VIH, this is VIL, and the slope is a V swing. So what is the slope of this waveform? That is VIH minus VIL, TR by. He is assuming a linearly rising wave, not exponential. This is an approximation he has made. Okay, and he says that every system is an RC system. So suddenly input is coming, you can model its output as a step response. Okay, where you say equations can be governed by these equations. I hope you all know network theory, circuit theory, step responses. Everybody knows step responses, representation in terms of step responses. The value of the current or voltage at T equal to 0 and the value at current and voltage at T equal to infinity. You all know that, and then you combine the values together and write a simple equation. Everybody knows. So that's what he is saying. He is assuming a single pole model, RC. Every inverter is modeled like a simple RC structure, has an R out and a C load. Accordingly, he writes its outputs in terms of these responses. At T equal to 0, it is V metastable. At T equal to infinity, it is some other value. Accordingly, he writes an equation. Okay. So, what's the probability that you have? So, first of all, when the clock edge has come, probability of under what condition you will have a metastability coming into picture. He says, what's the probability that when the data is sampled, your data is in a metastable range. Calculate the probability that data is in a metastable range when it is sampled by the clock. When it is sampled by the clock, because it could have been sampled here, no metastability. It could have been sampled here, no metastability. Because it is sampled here, it has led to a metastability. So according to him, the probability that when data is sampled, it is in a metastable state. It is in an unresolved state. That probability, now you can find out from here, very simple, it is only this range. This range out of this total, whatever time cycle is available to your T data. I am now looking at the T data. F data. Time cycle of the data waveform. One time cycle of the data waveform. So you have the data waveform changing here and the data signal changing here. So between these two you have one full time cycle. As I said, every data would be arriving at a certain rate. So there would be a T cycle attached to the data also. Remember F data we were saying, first of it will be T data. So within this T data, a metastability will happen if your data is sampled between VIH to VIH. It is completely 0 here. It is completely 1 here. Okay? If it is sampled here, doesn't matter. Only if it is sampled between VIH to VIL, there would be metastability happening. Accordingly, he computes the metastability range. So it is this time, this duration, okay, out of the complete T cycle of my data waveform, of my data signal. So next time again if it is sampled, it is sampled in a metastable rate, again it will lead to a metastability. Next time the next data comes, again if it is sampled in that range, there would again be metastability. That means your metastability now has to depend on the arrival of your data signal, that is F data, that is inversely proportional to 1 by T data. That is how T data is coming into picture. So it is VIH, so this duration, so VIH minus VIL upon the total V swing multiplied by T rise divided by the T data signal. T cycle is actually the time cycle for my data signal, the frequency at which it is changing. Okay, so this is the first probability, and then it may happen that your clock frequency may be operating at a very high frequency. So same data from here to here, multiple clock edges can come. Nobody says that. F clock can be operating at a very high frequency, whereas your input fed to it may be coming at a lower data rate. So larger the clock frequency, more is the chance of metastability. More is the chance of metastability. The probability that there you will get a metastability will get increased by the factor of F clock. By the factor of F clock, that's what he does. So if there is a multiple sampling happening within this range, there is a high chance of getting a metastability. Okay, so here is what we are getting is you multiply everything. You multiply everything now. This T data you will come as F data multiplied by F clock. Multiplied by F clock, and hence all your expressions will come in the form of, look very carefully. It comes in this form. This will anyway you have to multiply because probability it will decrease with the increasing waiting time. So this is what he gets finally, Rabi. This comes in form of the V swing, frequency of the data signal, frequency of the sampling clock, the time constant of my bistable element, and the waiting time that I am providing it to. And then this is the VIH to VIH. So if I compare the two together, the two expressions that we have got for MTBF, if I compare the two together, you can simply say it is everything is same, and this T hold minus T set of this window is actually what he is getting it as in terms of V swing upon VIH minus VIL. Rabe uses this expression, whereas if you look for other resources, they mostly work with this T setup to T hold window. Okay. So fine. So we can have a small example now. MTBF expression is with me, and we are given the sampling clock as 5 nanoseconds. T signal may be 50 nanoseconds, and rise time of my signal is say 0.5 nanoseconds, and tau of my system is 150 picoseconds, and VIH minus VIL is this. And waiting time that I am giving is 1 clock cycle, that is 5 nanoseconds, which is coming. I am not giving a waiting time more than, what is the MTBF? What's the chance of failure? So MTBF comes out to be, just plug in all the values, it comes out to be 23 years. So this is how you can make use of this expression in order to compute the robustness of your design. The robustness of your design. If this comes say few days, I will not be happy with it. Few days, few weeks, you will not be happy. Even 1 year, you will not be happy. Okay, so we want this to be as high as possible. So now, I want to increase this MTBF or decrease this probability of failure. So something which is in my hand, okay, apart from VIH, VIL, okay, this has only limited repercussions, limited impact. Something which is in my hand is waiting time. Again, I am not very, it's not that I am given an infinite amount of waiting time. Okay, but you have to somehow design a system which does not go into failure. Which does not go into failure. And we know that clock ticks every cycle. The system clock would be ticking, T clock would be ticking. Even then the system gets an input which is metastable. I have to somehow avoid system going into metastability or failure. How can you design such a system? Even though you know data is coming out to be metastable. In any case, I want system not to go into failure mode. So how would you design? So one thing is that you increase the resolving time. You increase the waiting time. Very first thing. But then you have waiting time of only one clock cycle. So I said, okay, I will not allow a data to latch into my system unless it is properly resolved. Whatever come, whatever be. I am ready to sacrifice my clock cycles. If in one clock cycle it is not resolving, I will give it another clock cycle. If still not resolving, I will give it third clock cycle. But I will not allow it to latch into, because if it latches, there would be a system failure, which I cannot tolerate. I am ready to sacrifice. That means every time I would keep on holding it. I will not allow it to move into the systems. So here you have the example of cascaded synchronizers. Cascaded design of a very first crude idea that you get in your mind, which is based on increasing the resolving time. That you have a design of cascaded synchronizers, that is multi-stage. So I have 1D latch, 2nd latch, 7-stage synchronizer, 4-stage synchronizer, 5-stage synchronizer. I design. So before it goes to the system, it has to go through 5 stages. Every stage requires 1 clock cycle. That means it will have a time cycle of 5 T cycle. I am giving it a waiting time of 5 time cycle. And I am hoping that it will resolve by 10. This is the concept which is used in design of cascaded synchronizers. Here you are wasting your clock cycles. Remember, you are wasting your clock cycles because your system is not giving you any output. Because unless the input gets resolved, you cannot produce any output. Okay, you are wasting the clock cycles. So we can have an example. So where you have only 1 synchronizer, then 2 synchronizer, then 3 synchronizers. So can you see MTBF was initially 30 milliseconds. Then it increased to 63 days for 2, and that increased to 30 million years for 3. So you can have a design of 3-stage cascaded synchronizer, a simple D-latch designed with 3 stages. You're designing a synchronizer for that. Simple, very simple example of simply increasing the time cycle and wasting your time cycle. Okay? Then somebody says, okay, this is okay. I'm not letting my system to go into metastability. I'm saving on that, but I'm wasting. Can you do something more? Can you think of something else? Can you think of something else? Contention detection. This is known as a contention detection. That you look at the data. If the data is metastable, do not allow it to latch. You will say, this is what I am doing in my cascaded also. I am giving it more time. Okay? So I will say, okay, I understand. But I still want a 1 clock cycle solution. I will not allow it to latch because it will cause a metastability to happen. Rather, I would look at my data and I will have an extra circuitry which will help it in getting stable. Now I have to help it. The moment I realize that this is unstable, this is metastable, I have to help my data to get stabilized. I will not allow it. I will not allow it to get latched the system. But then if I am giving it 1 extra cycle, then within that I am allowing it to or even not in that one cycle, the moment it arrives, I understand that it is a metastable, I immediately providing help to it. I immediately start providing help to it so that by the time one clock cycle the clock edge comes, the data is resolved and I am able to latch it onto the system. So you need to now provide an aid. Because we want one clock cycle solution, so there is a design overhead. There is a design overhead. So we need to actually start designing for one clock cycle solutions. Somebody said, okay, another approach. That okay, data is metastable and clock edge has come. So instead of not allowing the data to latch, why not delay the clock edge? Why not delay the? You design a fictitious clock edge then, which is different from the master clock edge. So delay the clock. These are known as delay the clock synchronizers. Actually, the concept is same. Concept is not changing. That if data is metastable, do not latch. How do you do it? Either by stopping the data and then adding it, or by delaying the clock edge, so that you get extra time. The data gets extra time to get this. It will lead. That's what I am saying. You need to design again. It will lead to skill. Every design that you make has its own repercussions, naturally. But then you are not working with. You have to now design a separate edge for yourself, which aligns itself with the master edge, which cannot be totally away or disaligned with the master edge. That is not possible. Otherwise, ultimately, at the last, when the data is latched, how will you align yourself to the system clock sequence? So we stop here, and I think one more class, 1.5 class more we'll be taking. So next class is on Thursday. Regular class will be. Okay.